Hello everyone, this is Professor Lee again. So today we are going to study chapter 2 and it's chapter 2.7. It's about measures of spread of the data. And we are going to split this chapter 2.7 into two parts, part A and B, and we're going to do it in two separate class. So, as I said, the title of each chapter is very important. So let's talk about this title and let's see what they are trying to do, in here. They try to measure something. So they want, at the end, they want a number. They want to measure and they want to come up with a number. Number that describe what? Describe the spread of the data. So what they're trying to do is this. Sometimes when you have a bunch of data, sometimes those data are very closely located to each other. They're not that far apart. Sometimes that you have a data that's really spread out there, really far apart from each other, right? But it's not really precise. It's not really mathematical to say, oh, this data set is kind of spread out. Oh, this data set is very concentrated. That's not mathematical at all. You can't. That really means really nothing in mathematics. You really need to come up with a specific answer. You need to come up with a number that describe whether these data sets are spread out or concentrated. And we are going to learn several different techniques of doing so, right? We try to measure. We want to come up with a number that describe the spread of the data. Now, one easy technique that we can use is what's called the range, right? So we try to, the same that we try to measure the spread. In other words, measure a variation, right? We want to measure the spread. We want to measure the variation. The same thing. And range would be one of those measure, one of those techniques to measure the spread of the data. Now, what is range? Well, you can read this, right? Range is what? Difference between the largest number and smallest number in the data set, in the data distribution. That's a range. So, let's talk about this example. Let's say you are a baker. You are running a bakery and you are trying to bake, I guess, blueberry muffin, right? So you need a supplier who supply the blueberry muffin from Maine. I guess Maine is famous for blueberry, I guess, right? So you weighted those container, right, the cartons of blueberry, and it's supposed to be 22 ounces, right? That's supposed to be the regular proper weight of the blueberry. Now, look at the supplier 1 and look at the supplier 2. Let's look at the supplier 1 first. Look at all these numbers. They are mainly 22, which is what you're supposed to be, what you're supposed to get, and you get 1 17 ounce and 1 27 ounce. So, if you want to calculate the range for supplier 1, what do? The highest number minus the smallest number, which is 10. So what does this 10 describe? It describes the range. What is range? Difference between the highest number and the lowest number. So That's a measure that describe variation. These data varies from 27 to 17 or 17 to 27, right? So then we just solve that question. We came up with a number that describes the spreadness of the data set. But you can probably guess the problem here, because supplier 2 also the smallest number and the biggest numbers are the same. So I guess range for supplier 2 is also 27 minus 17, which is 10. So range for supplier 2 is the same range. But as you can see, supplier 2 is kind of spread out. It's anywhere from like 19 to all the way to 25. It's all very spread out data. Supplier 1 is rather concentrated data. I mean, I can give you another extreme example. Like let's say sample 1, sample A, let's say, looks like, let's say 1, say 7, 7, 7, 7, 7, 7, 7, and 10. And sample B, let's say it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that, right? So, range for sample A and B, you can see that they are both 9 because the highest number is 10 and lowest number is 1. Highest number is 10, lowest number is 1. But you wouldn't say the spreadness of these two data sets, sample 1 and sample 2, are the same, right? Sample B is very spread out data. Sample A is highly concentrated data, around 7, right? So we try to describe whether these data sets are spread out or concentrated. But if we use range, it wouldn't capture concentrated data like this or spread out data like that, because both case range are the same, and that's a problem, right? So this range is simple and easy. However, it's not good enough to describe the spreadness of this data set in some case, right? So you can see that range formula right here, largest value and smallest value. So for the supplier 1 and supplier 2, they are both 10. However, as we discussed, supplier 1 was rather concentrated, supplier 2 was rather spread out. So, if you're a baker, when you are getting this supply, when you're getting this blueberry, you want a spread out type of supply, or you want a rather concentrated supply, supply. You want consistency, right? So you want a supplier 1, I guess, right? Okay. So it says it here, range are the same. However, supply 1 is more concentrated than supplier 2, right? Okay. So range is good. Why is it good? Because it's easy. Look at the formula. However, range is not really good enough because it wouldn't capture what's happening in the middle, right? They only care about the largest value and the smallest value. They wouldn't care about the middle value, right? What's going on in the middle, right? Between the largest number and the smallest number. So we have to come up with a different technique. Let me ask you this, and you can answer it, your own. What are we doing here? What's the main topic? What's the main question that we are after? Do you remember the title of this chapter? Title of this chapter was Measures of Variation, right? And what are we trying to do? We're trying to come up with the number that describe whether data sets are spread out or concentrated, right? That's what we are trying to figure out. And as we can see, range is simple and nice, but it's not good enough to describe what's happening in the middle. We need a more sophisticated technique. We need a better technique to figuring out what's happening in the middle. And those two techniques, or should we say those two measures, are variance and standard deviation. These are different measures that describe whether these two data sets are concentrated or spread out. And it's called variance and standard deviation. A fancy name, right? Okay, so let's discuss what they are. Before we actually get into the actual variance and standard deviation, let me give you a couple of symbols. And I rather want you to memorize this symbol. You know, this is online course, and you can have access to all the notes you want all the time. Technically speaking, you don't need to memorize anything. And I don't expect you to memorize all the formula at all. But there is one thing that I insist that you memorize is the symbol that I'm just about to give you, right? So here we go. And you can take a note if you want to, and you can memorize this symbol. And this is sample case, and this is population case. Population. The first thing was size. I mean, we discussed this in the previous chapter when we were dealing with the sigma symbol, but sample size, what symbol do we use? We use lowercase n, right? Population size, what symbol do we use? Uppercase n, right? And we also had a mean. Do you remember the mean, the average, right? So we had a different symbols for sample mean. Do you remember sample mean symbol? It was X with the bar on top, and we read this as X bar as well. So what's population mean? Population mean is mu, right? It looks like U with the long left leg, right? The mu. Now, next one is standard deviation. And followed by variance. And you guessed it right, and standard deviation variance is right here, right? And we are going to use a slightly different symbol for sample and population, right? First, for sample standard deviation, we use lowercase s. For sample variance, we use s with the square, lowercase s with the square, right? So you can see that, you know, the difference between the standard deviation and the variance is without the s square, without the square, and with the square, right? That's a sample variance and standard deviation. Now, population standard deviation is what? Is this symbol, and it's called sigma. Well, how does that look like? It looks like this. It looks like this, right? And this is sigma. It wasn't this the sigma? Yes, this was a sigma. So is this the sigma too? Yes. This is a uppercase letter. This is the lowercase letter for sigma, right? And this is a symbol for population and standard deviation. Now, can we guess what population variance symbol is that going to be? Right? Anyone? Right? Looking at these two, what will be the population variance? We guessed it right, sigma. square, right? So these table and these 8 symbol, I rather want you to just memorize it. I rather want you to just memorize this symbol, because we are going to refer to this over and over and over again, right? I rather want you to just memorize it. So whenever that they say, like say for example S, that you know they are talking about sample, and you know they are dealing with the sample standard deviation, right? So I rather want you to just memorize this. So far we know these two is to measure the variation, right? These two are the measures of variation. These two are the thing that describe the spreadness of the data set. So, and we'll talk about exactly how we are going to figure this one out. So, I mean, it says it right here. We need a measure of distribution, measure of variation. It's the same thing. Or it's just in plain word, it's a spread of the data around expected value, either x bar or mu. What does that supposed to mean? We know x bar, right? We just checked it right here. X bar is the mean. We know mu. Mu is the population mean. So why would they say spread around the expected value? So does that mean the expected value is same thing as the mean? You guessed it right. They are the same thing. So think about it. If the data are concentrated, what do you think it's the data concentrate around to? Concentrate around what value? The mean value, the average value, right? So if the data are spread out the same way, it's spread, where's the standard? Where's the middle? It's the mean value, and it's from the mean is spread out. If it's concentrated from the mean, that is spread out. So we need a measure that describe whether data set are far away from the mean or is it very close to the mean. And those two measures are called variance and standard deviation, right? And later we are going to see the formulas for variance and standard deviation. However, our wonderful calculator TI-84 will do all this calculation for us. But I want you to see the formula though, right? But you know, the actual calculation part, then the calculator does it for us. Okay, and we are about to see the formula for the variance and the standard deviation. But for the sample and for the population, we are going to use a slightly different formula for both variance and standard deviation. We are going to, and that difference is actually described here. For sample one, we're going to divide something, right? Divide value with something. When we divide, we're going to divide that by n minus 1 rather than n, right? But you will see it when you see the actual example and actual formula. Now, you know, this is the formula, and I can probably guess what you are thinking. Wow, this formula looks very scary, right? And it's really not friendly looking formula. So, well, let's you know, go over this formula together. First, it says these are population, variance, and standard deviation formula, right? And this left-hand side is called defining formula, and this right-hand side is called computation formula. So these two formula are the same thing. Well, they look different, but they will produce the same result. they will produce the same result. Now, why would they call this as defining formula? And why would they call this as computation formula? Well, they call this as a defining formula because when you look at this formula itself, it's kind of easier to see what they are trying to do. Right? It's easier to see what they're trying to do. So let's take a look at it together. Now, from this symbol, what do we know? What symbol do we know? I mean, we know this uppercase N. So what's uppercase N? Uppercase N right here. This is a population size, right? Population size. So at the end, we're going to divide the whole thing by the total number of population. Now, what does this X refers? This refers to each data point. Each data point. So each data point minus mu. What's mu? All right, so let me actually write it down. This is a population size, right? This mu is population mean. Population mean. This xi, each data point. So what do you think they're trying to do here? They're trying to do this. From each data point, you subtract the population mean. And once you get that number, you square it. And then you keep doing that, going one by one to cover every single data in the data set. Right? Keep adding. This is a sigma summation sign. This means adding up, right? Adding up. And then divide everything by the total number of population size. Right? So in a way, you are getting average square distance from each data point to the mean. That's what you're trying to find out here. Let me repeat that again. Average square distance from each data point from the mean. And that's what variance is all about, right? And why would they square though? Because, you know, sometimes that plus difference and minus difference will cancel out each other, right? And you don't want that, right? Even if they're far apart, it looks like there's no difference between these two, and you don't want that. You want to capture all those differences. That's why they are squaring. Now, what I'm explaining now is very technical term. Do we absolutely have to understand 100%? Well, it's good if you can understand 100%, but it's okay if you cannot, because at the end we're going to do this calculation in calculator, and I don't even recommend you to use this formula if you have to do it manually. I would rather want you to use this computation formula, right? If you have to do it manually. But we'll get to this computation for a short while. What about this standard deviation? Now, what do you think is the similar and difference between these two? Well, take a look at it. You tell me what's different and what's similar. First of all, this one has a square because it's a variance, and this one doesn't have square because we are calculating the standard deviation value. Now, what else is different? Well, this one has this sign. Does anyone know the name of this symbol? This is called square root. Right? Square root. That's the name of this symbol. It's like reverse way of squaring. That's what this is. Square root. What does that do? It go back it reversed the squaring effect, right? That's what this ones do. So if you want to figure out the standard deviation, you need to figure out the variance first, and then take the square root of that variance value, then you will get the standard deviation value, right? So find the variance value first, then take the square root, and that will give you the standard deviation value. Right? Let me repeat that again. Find the variance value first. Take the square root of that result, variance, and the square root of that variance is going to be the standard deviation value. Right? So that's a defining formula. Computation formula, however, look at this one right here. What does it do? That's sigma means adding up. Adding up what? You square each data point, then add up. So let me say it in here. Square each data, then add the result. Right? You square. So this part is you square every data point and you add them up. After you square it, you add them up. That's what this first part is. What about this part right here? This part, circle that, and that's this one right here. This part is add all the data, then square the sum. So this part right here is saying you gotta add all the data points first, then you square the sum. That's what this part is about. So this first part right here, you square first, then add. This one right here, you add first, then square. And of course, after you add them up and you divide that by n. Again, what's n? That's the population size. And then from the first part, you subtract the second part and then divide everything by n again. That's a population variance and standard deviation, and these are computation formula. Now, going back to the defining formula, look at this part right here. You have to use the population mean. That means you have to calculate the mean value first, then put that in this formula, and you have to go one by one. What about the second formula, computation? Do you have to find the mean first? No, not at all. You don't have to find the mean first. You can just put it in this formula and you can find it. And once you find the variance, same deal here to here. You just need to take the square root and you got the standard deviation value, right? Exact same technique. So, sometimes your population mean is a nice clean number like 17, but sometimes not. Sometimes your mean value from the population could be 17.1742074, something like that, some horrible long number, and it's not even an exact number. So if you have like horrible mean, then you have to deal with all this rounding off error when you keep squaring it and adding it, all that. But not in here. You don't need to do that. You don't even need to figure out the average. You don't need mean here. You can just put it in that formula and that's it. right? Now, these are sample variance and sample standard deviation. Now, take a look at this formula, and let me go back to the previous and this formula, right? As you can see, these formula are almost identical, right? Almost identical. For defining formula, instead of using mu, we use x bar. Why? Because x bar is the symbol for sampling. Instead of uppercase N, we use lowercase n. However, if you go back to the previous, when you divide at the end, it was all n only, never n minus 1. It was all n for population. But for sample, it's always you divide by n minus 1 at the end. N minus 1 at the end. You know what? In page 8, I believe, that's what they mean by divide by n minus 1 for sample, right? If the data form is a sample rather than population, then you got to divide that by n minus 1. And that's what they mean by dividing that by n minus 1 here. Again, this one has defining formula and also computation formula. Pretty much the same deal. And I rather want you to use computation formula if you have to do this manually, because you don't have to figure out the mean first. You can just put, and so this one right here is the same deal. You square each data and add. This one, you add all the data, then square. Just like, let me go back to the previous, just like these two, right? Just like this, is the same thing. And divide by n here, but the final division right here, it's going to be n minus 1, right? So this is the formula to figure out the sample variance and sample standard deviation. I wouldn't say this is a friendly looking formula, but it's not that horrible if you really take a look at it, take your time and try to figure out. And fortunately or unfortunately, if as we progress, this is not the most horrible looking formula. We will have a lot more interesting formula later on. But the good news is we are going to use TI-84. TI-84 does all the work, right? So we don't really have to worry about that. All right, let's do this example. So this Big Blossom Greenhouse is a company developed extra large rose for Rose Bowl parade, right? And they have this random sample of, I guess, the rose bowl diameter, right, in inch. And I mean, it's a nice story, but I don't really care. I really care about these numbers, right? So we have 1, 2, 3, 4, 5, 6 different numbers. Again, what are we trying to, what's the big topic here? What are we trying to figure out, right? We're trying to figure out the spreadness of this data. Now, let me ask you this question. What would you say? Would you say this data sets are rather spread out data, or is it concentrated data? What would you say? All these numbers, right? Do you think these are spread out data, or do you think this is a concentrated data? I'll probably say this is rather spread out data. I don't think this is a concentrated. But like I said, just by saying, oh, this is kind of spread out data, that doesn't mean anything in mathematical world. You need to come up with a number that describe whether this is spread out or concentrated. Remember we learned range? Range was what? The highest value minus the smallest value, in this case 8. 8 is the range of this data set, but range is simply not good enough to describe whether this entire data sets are spread out or constant. So this question says, use computation formula to find the sample variance and sample standard deviation. Now, is this a sample data or is it population data? Because it's a sample data, we're going to use this formula for sample. If it's a population data, we are going to use this formula. I mean, it says it right here. Following sample. This is a sample data, right? So sample data, I just rewrote that sample variance formula right here and sample standard deviation formula right here. So this is how it works. This part right here, like I said, I described in here. What was our original data? 2, 3, 3, 8, 10, 10. So 2, 3, 3, 8, 10, 10. This was our original data. You square each one of these, like we did it in here, and then add them up. That's what this part, right? And you got 286. What about this part right here? This part right here, right? We go all the way to here. So this one, you add these data, right? That's what you did. You add this data, which is 36, then you square it, right? Then you square it, right? So let me actually do 36 square. What do you get 36 square? Well, 36 square is actually 1,296, right? That's 36 square. Now, so that part right here is going to be 1,296. But you gotta divide that by n. What's n? Sample size. That means we have 1, 2, 3, 4, 5, 6 different data points. That's why it's going to be 6 right there. So 1,296 divided by 6 is going to be 216. And so, you know, you gotta be careful in what order that we are doing this calculation. You do this calculation first right here, boil down to a single number, then you do this subtraction first. So I mean, you know, 286 minus 216. So if I just, that would be 70 over 5. 70 over 5 is 14 right here. So is this a variance value or standard deviation value? What do you think? That's a variance value right here, S squared. And how do you get the standard deviation value? Well, like I said, all you need to do, take the square root and hit return, and that's the standard deviation value, right? So this is the standard deviation. And this is the variance. This is the variance value, right? And this is how we calculate variance and standard deviation for this sample data, right? Okay, and let me show you how we actually can do this in our TI-84 calculator. First, you are going to press STAT button and it'll open up this window. And in the window, this window, you choose this. I mean, it's highlighted here, so all you really need to do is just hit return. And it'll open up this table. So in the table right here, you type up these number one by one, right? So, 3, 2, 3, 3, 8, 10, 10. Then you put the stats again. You hit the stats again. Then it'll show you this window. Then you move your cursor to here, calculate, and you choose one variable. And it'll say one variable, and it'll usually do it like that. And it'll ask the frequency. You don't have to worry about it. Just hit return and compute return. Then it'll open up this all calculation. Look at what was the answer? All right, let's go back. What was the answer? The answer was 14 and 3.74, right? 14 and 3.74. So 3.74, right? 14 and 3.74. This is not technically correct because it only has up to 10. We need to put one more 10 here to get the correct answer. But you see the general technique to have this, right? You see the general technique to have this. Now, actually, we are going to do this together, and I'm going to show you how to do this together. So let me get out of here. And okay. So I am sharing the full screen, right? Full screen here, so that you can see these. You can see this, and you can also see my calculator. So we put the calculator on, clear this, and hit the stats, and hit edit one. Let me clear all this. So I'm going to move my cursor to highlight this and hit clear once. Don't hit clear 2 times. It'll delete the L1 whole column. So just hit once. And if you do, you have to reset the whole calculator, right? So then L1 column is clear. I'm going to put 2, enter. 3, enter. 3, enter. 8, enter. 10, enter. Another 10, enter. So I put all 6 data points, and then hit stats again, move to calculate, one variable that I'm going to choose. It says my list is in L1, yes. Frequency, I don't have to worry about it, so just keep hitting enter and calculate. There you go. Remember 3.74, right? In this calculation right here, right? So we have this calculation right here, and we got the same answer here. And remember last chapter, we talked about the 5-number summary from minimum to the maximum. It's also here as well. Let's go back to this result though. So this X bar, what is it? This is a sample mean. So they think this is a sample data. I mean, they always think any data is a sample data, right? So that's that. And when you add, look at this symbol, when you add all this, when you add these data points, and we have 36, when you square and add, you have 286 right here. And they give you 2 options. This S means this is a sample data. This is sigma, means if you think this is a population data, this would be the standard deviation for that data, right? I mean, they didn't give you the variance though, right? So if you want the variance, what you can do, you can take this number and you can square it. Not the square root, you can square it to get the variance. But The reason why they only give you the standard deviation is that in real life, you hardly use the variance value. You always use the standard deviation value, right? That's why they are giving you this, right? Okay. I am going to go here. Okay. Okay. So we talked about this. And let's say using the TI-84, find the population and sample standard deviation for these following data point, right? So it's the same thing, right? It's the same thing. Like I said, it's the same thing. We let me get out, right? And let me see. So let me actually share that full screen view. Okay, so these are the data point. So if we do it together, we're gonna go to stats, edit, and we're gonna, let me clear this. Clear, enter, and 41, enter. 38, enter. 39, enter. 45, enter. 47, enter. 41, enter. 44, 44, enter. 41 again, enter. 37, enter. 42, enter. So we put all 10 data. Go to stats again, move to calculate, one variable, enter, enter, enter. Right here, right? I mean, you see the answer in our screen right here, right? So let me share our PDF, I mean the PowerPoint, right? So there you go. This is our answer, right? Because they say, find both population and sample standard deviation for the following data. There you go, right? Now, data value that 2 standard deviation away from the average is just on the borderline for what many statisticians would consider that is too far away from the average. And we call that value as unusual value. Let me repeat that again. So idea is this. If a certain data point are 2 standard deviation away from the mean to the top and the bottom, right, in both directions, then that's unusual if it's not between those two values. So how do you calculate the usual and unusual? Let's say average value is this. When you calculate the mean, let's say this is the mean. And let's say you also calculate the standard deviation value. And let's say it's 2.97. I think these are these values right there, right? Anyway, now let's say these are the two values. Then you put it in the calculator. From the mean, you do minus 2 times the standard deviation, and you do the mean plus 2 times the standard deviation, and it'll give you these two numbers, right? This and this. So when you look at these data sets, see if any one of these data is not in between these two numbers. If any one of these data are not in between these two numbers, and we consider that as a unusual data. In this case, there's no number, it's not in between. So we don't think this is unusual data, right? You know what, I think, right, okay. I think we might have used a different mean because this was the mean from the population. We supposed to use 3.13 and we would have got a different result. Let me just quickly do this though. 41.5 minus 2 times 33.13. You know, because if we think this is a continuing example, then we could have done 41.5 minus 2 times 3.13, that's 35.24. And if you do the plus, so if you do 41.5 plus 2 times 3.13, that would have been 47.76, right? So it's a similar value, not that far from this. And again, you check any one of these data points, it's not between these two, right? Then, so in this case, we really do not have any unusual data. But let's say this was like, 52, for example. If this was a 52, then 52, this value is not between these two numbers. So we consider that as an unusual value, right? Okay. So figuring out the quartiles, this is a pre-calculus class exam result. Calculate the following data: sample mean, sample standard deviation, median. Median is Q2, right? First quartile and third quartile, this is Q1, Q3, and IQR. So, we put it in all this value in the calculator, right? You do the same thing, do the stats and put it in that, L1 column right here, put all these numbers in this column. You hit the stats again, and then you choose one variable, and then hit enter, then you will see this result. This one is the mean here. Sample standard deviation, right here, sample standard deviation. The median, where's the median? Median is right here, 73. First quartile, 61. Third quartile, 90. IQR was what? Q3 minus Q1, right? 90 minus 61, 29 is IQR, right? So if you use the graphing calculator, like I said, it's very, very easy, right? Now, same data, find the outlier. Remember that outlier question? Remember this was the formula? So from Q1, from 61, minus 1.5 times IQR. IQR was, remember, 29. And then you have this lower fence. Upper fence from Q3 plus, this time is plus 1.5 times IQR. And you get this. So these two are the lower bound and upper bound for outlier. So you're going through these data set. Any number is not between this. Well, this is the lowest number, this is the highest number. I think every single data fall into this. That means do not have outlier, right? But if you have any data point, if this, for example, 160, if this was like 160, then that would have been the outlier, right? Okay, so this was relatively long, and chapter 2.7, the part B, that we are going to do it in next video, right? Okay, so that's the wrap for 2.7 part A.